Tonight we are going to talk about the strangest fact about being alive in a universe that obeys the laws of physics. The fact that you have never, not once in the entire history of your existence, been still. Not for a single second, not for a single moment. Right now, while you sit or lie or stand and listen to these words, your body is moving in multiple directions at once, at speeds that would terrify you if you could feel them. The planet under your feet is spinning. The planet is orbiting our local star. The star is sweeping around the center of the Milky Way galaxy at 514,000 miles per hour. And the galaxy itself is being pulled by something we cannot directly see at 1.4 million miles per hour with respect to the oldest light in the universe. You cannot feel any of it. Your senses are not built to detect uniform motion. The stillness you have always assumed you possess is an illusion, produced by the fact that everything immediately around you is moving along with you. You are inside the motion. The motion has carried you for every instant of your life. And tonight, we are going to follow it. We are going to walk through the layers of motion that surround you, from the spin of your planet, to the orbit of your solar system, to the sweep of the galaxy around its own center, all the way out to the largest known structure of matter in our cosmic neighborhood. We are going to discover what is pulling us. We are going to discover what is pushing us. We are going to learn the name of the cosmic supercluster we live inside, a name that was only given to it 11 years ago. We are going to meet the gravitational anomaly that has been tugging on our entire region of the universe for billions of years before there were eyes on Earth to detect it. And we are going to follow the motion all the way to its eventual end. By the end of this video, you are going to understand exactly how fast you are actually moving in every direction at once. You are going to understand what is doing the pulling. You are going to understand the contest between gravity and dark energy that determines the long-term fate of everything. And you are going to understand why the universe will eventually run out of motion entirely, and what that ending will look like on a timescale so long that human imagination cannot comfortably hold it. And you are going to arrive at a strange conclusion. The end of all this motion, the place every spinning, orbiting, drifting thing in the universe is ultimately heading, is the one state you have never personally experienced. Stillness. Real stillness. The kind no living thing has ever known. The kind that waits at the very end of time, when every form of motion has finally given up, and the universe at last achieves what you have spent your entire life imagining you already had. So let us start at the beginning, with your body, with the floor under your feet. If you are reading or listening to this anywhere on the surface of the Earth, the most basic motion happening to you right now is the rotation of the planet on its axis. The Earth spins once every 23 hours, 56 minutes, and 4 seconds. From the perspective of someone floating in space, watching from a fixed point, your patch of ground is moving eastward. Always eastward. The motion never stops. How fast you are moving depends on your latitude. At the equator, the Earth's circumference is about 24,900 miles. The planet rotates through that full circumference once per day. The math is simple. At the equator, the surface of the Earth is moving at roughly 1,040 miles per hour. That is faster than the speed of sound. If the atmosphere were not also moving along with the planet, the wind from this rotation would be a constant supersonic hurricane. At higher latitudes, the rotational speed is slower. The cosine of your latitude multiplies that equatorial speed. At 45 degrees north or south, you are moving at about 735 miles per hour. At the poles, you are not moving at all relative to the rotation. You are just spinning slowly in place, completing one full rotation per day, the way a coin spinning on its edge eventually slows and falls. For most of the inhabited surface of the Earth, the rotational speed of the ground is somewhere between 500 and 1,000 miles per hour. That is faster than a commercial jet, faster than the muzzle velocity of many bullets. And yet, you cannot feel it. You have never felt it. No human has ever felt it. We feel the wind when a car moves at 60 miles per hour because the air outside the car is not moving with the car. We feel the lurch of a roller coaster because the body experiences acceleration even when it cannot measure speed directly. But the rotation of the Earth produces no such sensation because everything around us is rotating along with us. The atmosphere, the buildings, the oceans, the mountains, our blood, our bones. Everything moves at the same rate, in the same direction, at the same time. There is no relative motion for us to detect. This is the reason humans believed, for most of our history, that the Earth was stationary. The motion of the stars at night was easy to see, but the motion of the ground beneath our feet was not. Our senses are not built to detect uniform motion. They are built to detect change. When everything moves together, change disappears from our experience, and we mistake motion for stillness. This is the first lesson of cosmic motion. Stillness, as you have always experienced it, is not a physical state. It is a cognitive illusion we invented to cope with the fact that we cannot feel the things our bodies are doing. Your brain reports stillness because the differences between you and your immediate environment are zero. The motion is still there, you just cannot perceive it. This same principle holds inside an aircraft cruising at 500 miles per hour. If the flight is smooth and the windows are closed, you cannot tell you are moving. You can stand up, walk to the bathroom, pour a drink, all the same activities you would do in a stationary room. The aircraft's motion is undetectable from inside because everything inside the aircraft, the air, the seats, the floor, the passengers, is moving at the same rate. If a sudden change happens, turbulence, a sharp turn, a rapid descent, your body immediately notices because the change creates a difference between what your body is doing and what your inner ear expects. But uniform motion by itself produces no sensation. This is a discovery that took humanity centuries to fully grasp. The realization that uniform motion is undetectable from within is one of the foundational insights of classical physics formalized by Galileo in the 17th century. Galileo used the example of a ship sailing at constant speed across a calm sea. To a person inside the ship feels stationary. They can drop a ball and it falls straight down. They can throw a ball into the air and it comes back to their hand. They can pour wine and it flows into the glass as expected. None of these activities would reveal to someone trapped inside the ship without windows that the ship was moving at all. The same physics applies inside the ship as applies on land. There is no experiment you can perform inside the ship that distinguishes between the ship moving uniformly and the ship being at rest. This principle, sometimes called Galilean invariance, was later generalized by Einstein into the principle of relativity that underlies modern physics. The laws of physics are the same in every reference frame moving at constant velocity. There is no privileged frame, no special state of being at rest. What you call rest is just a frame of reference. The Earth is a frame of reference. The solar system is a frame of reference. The galaxy is a frame of reference. Each of them feels like rest from inside because the motion is uniform within each frame. The reference frame of the cosmic microwave background, the average rest frame of the universe as a whole, is also just a frame. Our motion through it is 630 kilometers per second. But our motion through it does not feel like anything, because we share that motion with everything immediately around us. If the rotation of the Earth were the only motion you were doing, the situation would already be strange. But it is not. The planet itself is moving. Earth is orbiting the Sun in a vast elliptical path, traveling at an average speed of about 67,000 miles per hour. That is roughly 19 miles per second. If you took one breath while reading the last sentence, you traveled about 300 miles during it. The orbit takes 1 year to complete. We have built our entire calendar around it. The seasons we experience, the year we celebrate, the cycle of birthdays and anniversaries that structures human life, all of it is a function of the planet's position along this orbital path. You have completed this orbit once for every year of your life. If you are 30 years old, your body has traveled approximately 15 billion miles around our local star. The distance you have personally moved through space, just by sitting on the surface of the Earth while the Earth has done its work, is more than the diameter of the entire solar system, traveled many times over. And again, you have not felt it. You have not felt yourself accelerate when the Earth was closer to the Sun and moving faster. You have not felt yourself decelerate when the Earth was further from the Sun and moving slower. The change in your speed across the course of a year is about 1 kilometer per second, the difference between Earth's velocity at its closest point to the Sun, called perihelion, and its furthest point, called aphelion. That change happens slowly, smoothly, across months. It is far below the threshold of any sensation your body could produce. This is the cosmic principle in its simplest form. Motion that surrounds you, that includes you, that you share with everything around you, becomes invisible. It is not that you are unable to detect it, because your senses are weak. Your senses are not weak. They are precisely calibrated for the situations that mattered for your survival on the African savanna. They are not calibrated for the question of whether the rocks under your feet are sweeping you through space at 17 miles per second. Evolution had no reason to give you the ability to feel that. The rocks were going to take you along anyway. Whether you were aware of it made no difference to whether you survived. Now we have to take the next step outward. Because the Sun is not stationary either. The Sun is moving. And it is moving very fast. Imagine looking down at the Milky Way galaxy from above, the way some illustrations show it. A flat, rotating disk with 2 main spiral arms curling out from a central bulge and a few minor arms threading through the disk. The disk is about 100,000 light-years across. The Sun sits in one of the minor arms, called the Orion Arm, about 26,000 light-years from the center. From your vantage point above the galaxy, the disk would be rotating, slowly, majestically. The stars in the inner regions move faster. The stars in the outer regions move slower. Each star traces a vast circular orbit around the center, governed by the combined gravity of every other star and every cloud of gas and every halo of dark matter inside its orbital radius. The Sun is rotating with the rest. It is carrying you and the rest of the solar system along with it. The speed at which the Sun moves around the galactic center in its huge circular orbit is about 514,000 miles per hour, 230 kilometers per second. That is fast enough to circumnavigate the Earth's equator in about 3 minutes. Fast enough that, if you could somehow ride along on a spacecraft moving with the Sun, you would cover the distance from London to New York roughly every 9 seconds. And like every other motion you have experienced, you do not feel it. The atmosphere is moving with you. The solar system is moving with you. The planet is moving with you. Your body is moving with the planet. There is no relative motion, no acceleration, no change. The motion is invisible because it is total. The Sun has been doing this orbit for about 4.5 billion years, ever since it formed. In that time, it has completed roughly 20 full orbits around the galactic center, 20 laps of the Milky Way. That is your Sun's cosmic age, measured in galactic years. A galactic year is the time it takes the Sun to complete one full orbit around the center of the Milky Way. It is sometimes called a cosmic year. The duration is about 225 million Earth years. Think about that for a moment. 225 million years. The last time the Sun was in the exact position it is in right now, the last time it occupied this point in its orbit around the galaxy, what was happening on Earth? The dinosaurs did not exist yet. They would not appear for another 40 million years. The continents were arranged differently. The supercontinent we now call Pangaea was just beginning to break apart. The Permian-Triassic extinction event, the largest mass extinction in the history of life on Earth, had just happened. 96% of marine species had been wiped out. 70% of terrestrial vertebrates were gone. Life was, for the first time in hundreds of millions of years, starting over almost from scratch. That is what was happening on Earth the last time the Sun was at this exact point in its galactic orbit. The last time the cosmic year was where it is now. The galactic year is so long that it makes ordinary years feel like nothing. Human history, all of it, every empire, every war, every invention, every recorded thought, fits inside about 1/20,000th of a single galactic year. The pyramids of Egypt were built about 4,500 Earth years ago. In galactic terms, that is about 1/50,000th of one orbit. The pyramids, in the timescale of the Sun's motion through the Milky Way, were built yesterday. You have lived through some small fraction of a single galactic second. The Sun has barely moved in its orbit during your entire life. You will not live long enough to see it move noticeably. None of your descendants will. Even if humanity persists for another million years, the Sun will have completed only about 1/200th of a single galactic orbit in that entire span. This is the strange double experience of cosmic motion. The speeds are enormous, 514,000 miles per hour, and yet, in the context of the distances involved, those speeds are nothing. The galaxy is so large that the Sun's blistering velocity, applied for the entire lifetime of the solar system, has produced only 20 laps. 20. Take a moment to hold these numbers in your mind. The Earth is rotating you at 1,000 miles per hour. The Earth is orbiting the Sun at 67,000 miles per hour. The Sun is orbiting the galaxy at 514,000 miles per hour. Each motion is invisible to you. Each motion is happening right now. Each motion contributes to the path you are tracing through the universe. But the motions are not independent. They are nested. The Earth rotates, but the rotating Earth is also orbiting our local star. The star moves through the galaxy, but the moving star is also carrying the Earth along. Your actual path through space, if you could draw it on some impossibly large map, would not be a circle. It would be a spiral nested inside another spiral, nested inside another, nested inside something larger still. And that something larger is where we are about to go. Because the solar system's motion through the galaxy is not, by itself, the end of the story. The galaxy is not floating in some quiet vacuum, rotating peacefully in place. The galaxy itself is moving. It is being pulled by something massive, by something we cannot see directly, by something that has been tugging on our entire cosmic neighborhood for the entire history of our civilization, and most of the history of life on Earth, and most of the history of the planet itself. The Milky Way is falling towards something, and that something has a name. In the 1970s, a team of astronomers began to notice something strange about the way galaxies in our part of the universe were moving. The universe is expanding. This had been known since the 1920s, when Edwin Hubble showed that distant galaxies are receding from us, and that the further away a galaxy is, the faster it is receding. This recession is not a real motion through space in the conventional sense. It is the stretching of space itself. The galaxies are not moving outward like fragments from an explosion. The space between them is growing. If the universe expanded perfectly uniformly, every galaxy would be receding from every other galaxy at exactly the rate predicted by the Hubble flow. But the universe does not expand perfectly uniformly. Galaxies have their own additional motions, called peculiar velocities, which are independent of the cosmic expansion. These peculiar velocities arise from gravity. A galaxy near a massive cluster will be pulled toward the cluster by the cluster's gravitational field. A cluster near a larger cluster will be pulled toward the larger one. The peculiar velocities are the gravitational fingerprints of every mass concentration in the local universe, written into the motions of every galaxy near them. In the late 70s and early 80s, astronomers measuring these peculiar velocities began to find that hundreds of galaxies in our part of the sky were all moving in the same direction at the same time, at speeds that could not be explained by anything they could see. There was no obvious mass concentration in that direction. There was, in fact, no obvious anything in that direction. And yet the galaxies were flowing, streaming, falling gravitationally toward something. A group of 7 researchers, who would later become famous in the astronomy community as the 7 Samurai, published a paper in 1987 describing this collective motion. The data showed that the entire local group, the cluster of galaxies that includes our Milky Way and Andromeda, and about 50 smaller galaxies, was moving at hundreds of kilometers per second relative to the cosmic microwave background. The direction of that motion did not point toward any object we could see. It pointed deeper, towards something hidden. The 7 Samurai gave it a name. They called it the Great Attractor. The name alone tells you something about the situation. They did not call it a galaxy. They did not call it a cluster. They called it the Great Attractor because what they had found was not, in the first instance, an object. It was a gravitational anomaly, a pulling, a direction in the sky where everything seemed to be flowing, even though nothing visible was there to do the pulling. For years afterward, the Great Attractor remained one of the strangest entities in modern cosmology. It was real. The data was clear. Hundreds of galaxies were moving toward a specific region of space at speeds that demanded a vast gravitational source. But the source itself was invisible. The reason it was invisible turned out to be embarrassingly simple. The direction of the Great Attractor, the patch of sky toward which everything was falling, happened to lie almost directly behind the central plane of our own Milky Way galaxy. The Milky Way is a flat disk. From inside the disk, looking out, we can see the rest of the universe in almost every direction. Almost. The exception is the band of the sky that lies along the plane of the galactic disk itself. When we try to look in that direction, our view is obstructed by the dust and gas and stars of the disk we live in. This obstruction has a name. It is called the zone of avoidance. It is the part of the universe that our own galaxy hides from us. About 20% of the entire sky lies behind it, and the Great Attractor sits inside the zone of avoidance. For 30 years, The Great Attractor was a thing we knew existed because of how everything around it moved, but a thing we could not see because our own galaxy was in the way. To detect what was actually there, astronomers had to use forms of light that could pass through the dust. Infrared radiation, X-rays, radio waves. Each form of light revealed a little more of what was hidden. By the early 2000s, the picture had begun to clarify. There was a massive galaxy cluster sitting in the zone of avoidance at a distance of about 220 million light-years. It was called the Norma cluster, or Abell 3627 by its catalog name. The cluster contained thousands of galaxies. It was comparable in mass to the better-known Coma cluster, and it sat almost exactly where the Great Attractor was supposed to be. For a while, astronomers thought the Norma cluster was the Great Attractor. The mystery, they thought, was solved. The pull on our local group came from this enormous cluster of galaxies hidden behind the disk of our own Milky Way. Then they did the math more carefully, and the Norma cluster was not quite massive enough. The pull on our region of space was stronger than even the Norma cluster could produce. There had to be something else, something deeper, something further away, but more massive, contributing to the gravitational flow. The answer, when it came, was a structure even more enormous than the Great Attractor itself. About 650 million light-years from Earth, much further away than the Norma cluster, lies a concentration of galaxies so vast that it dwarfs anything in our local cosmic neighborhood. It is called the Shapley supercluster, or sometimes the Shapley concentration. It was first identified in the 1930s by the American astronomer Harlow Shapley, who noticed an unusual density of galaxies in that particular direction. For decades, the discovery was largely forgotten. The Shapley concentration was far away, and there were closer mysteries to solve. In the late 1990s and early 2000s, as astronomers tried to account for the Great Attractor's apparent mass deficit, the Shapley supercluster came back into focus. The mass concentration there is enormous, roughly 10,000 trillion times our home star's mass. It is one of the largest known structures of matter in the local universe, and it sits in the same general direction as the Great Attractor, just much further away. What had looked like one gravitational mystery turned out to be at least two. The Norma cluster pulls on us. The Shapley concentration further behind it also pulls on us even more strongly. Together, these two structures, along with smaller contributions from other galaxy concentrations in the same general direction, account for most of the observed motion of our local group through the cosmic microwave background rest frame. That motion is fast. The local group is moving at about 630 kilometers per second relative to the oldest light in the universe, 1.4 million miles per hour. The direction is roughly toward the Shapley concentration, with the Norma cluster contributing a closer, lesser pull along the same line of sight. Take a moment to absorb that. The Milky Way galaxy, containing 400 billion stars, with the entire local group of 50 or more galaxies around it, is being gravitationally pulled toward a concentration of galaxies 650 million light-years away. The pull is so strong that the entire region of space we live in is flowing in that direction at speeds far exceeding anything you could measure on a human scale. And we have no choice in the matter. The pull has been there since long before there were eyes on Earth to detect it. The pull will be there long after the last human eye has closed. But this pull is not isolated. It is part of something larger, because the motion of our local group is not the only flow. Every galaxy in our region of space is moving in patterns that, when mapped, reveal a vast underlying structure, a river system, in 3 dimensions, where every galaxy is a drop of water, and the water is flowing. The picture that emerged from decades of mapping these flows, by teams led by astronomers like R. Brent Tully at the University of Hawaii and Hélène Courtois at the University of Lyon was completely unlike anything astronomers had previously imagined. Before 2014, the standard map of our cosmic neighborhood was relatively simple. Earth was in the solar system. The solar system was in the Milky Way. The Milky Way was in a small cluster of galaxies called the local group. The local group was in the outskirts of a larger structure called the Virgo supercluster, sometimes also called the local supercluster. This was the address most textbooks gave for the location of our planet. Earth, solar system, Milky Way, local group, Virgo supercluster. That address turned out to be wrong. Or rather, it turned out to be incomplete. The Virgo supercluster, in the new understanding, is not the highest level of organization our galaxy belongs to. It is just one component of something much larger, something that was discovered by mapping the gravitational flows of galaxies and finding the boundaries where the flows changed direction. The new structure has a name in Hawaiian, chosen by the team that discovered it to honor the Polynesian navigators who used the stars to cross the Pacific Ocean. It is called Laniakea. The word means immense heaven. Before we follow our cosmic address out to Laniakea, we have to pause and ask what the Great Attractor actually is. Not as a mathematical pulling, as a physical place. What does it look like? What is happening there? If you could somehow ride a spacecraft to the Great Attractor, leaving the Milky Way behind and traveling along the line of motion that our local group is currently following, what would you find when you arrived? The first thing you would encounter, at about 220 million light-years, is the Norma cluster. It is a dense, massive cluster of galaxies with thousands of members. The galaxies at the center are mostly old, mostly red, mostly elliptical. They have been gravitationally interacting for billions of years, merging and colliding and stripping each other of gas. The cluster is hot, in the technical sense. The space between its galaxies is filled with extremely hot gas, hundreds of millions of degrees in temperature, glowing in X-rays. This hot gas is what astronomers first detected when they began penetrating the zone of avoidance with X-ray telescopes. The cluster does not look peaceful. It looks like a battle that has been going on for a quarter of the age of the universe. To grasp what is happening inside the Norma cluster, consider what the universe is doing on smaller scales when galaxies collide. When two large galaxies merge, almost none of their individual stars actually hit each other. The distances between stars are too great. The Milky Way contains about 400 billion stars. But the average distance between two stars near our position is more than 4 light-years. Stars are point sources of light, scattered across enormous volumes of mostly empty space. When galaxies pass through each other, the stars sail past each other like dust particles released into a stadium. The probability of any one star hitting any other star during a galactic collision is essentially 0. But the gas is a different story. Galaxies are not just stars. They are also vast clouds of hydrogen and helium gas with smaller amounts of heavier elements. The gas fills the spaces between stars in volumes large enough that when two galaxies collide, the gas does collide. Streams of gas from one galaxy run directly into streams of gas from the other. The collision heats the gas to enormous temperatures. The pressure waves trigger Li-Ho star formation. The angular momentum of the system is rearranged. Over hundreds of millions of years, the two galaxies become entangled, lose their original spiral structures, and eventually settle into a single, larger, elliptical galaxy. The Norma cluster has been hosting these kinds of mergers for billions of years. The cluster's hot X-ray emitting gas is the cumulative product of all the galactic collisions, all the supernovae, all the violent stellar deaths, all the merger events that have happened in this region of space. The X-ray glow is the memory of everything that has fallen into the cluster, compressed and heated by the cluster's gravity. If you kept traveling past the Norma cluster, deeper toward the Shapley concentration, you would pass through several more clusters of galaxies, each one massive in its own right, each one contributing its small share of gravitational pull to the flow you are riding on. The space between the clusters is mostly empty, but threaded with strands of dark matter and thin filaments of intergalactic gas. The structure of the universe at this scale is not a uniform sea of galaxies. It is a web, a cosmic web, with galaxies clustered at the nodes and along the filaments, and vast voids in between. About 650 million light-years from Earth, you would reach the Shapley concentration itself. This is the deepest known mass concentration in the local universe. Thousands of galaxies, grouped into dozens of clusters, organized into a single vast supercluster of superclusters. The mass is so great that it is the dominant gravitational influence in the entire region of space that includes our local group. Most of the apparent motion of the Milky Way through the cosmic microwave background can be traced back to the pull of the Shapley concentration. And here is the strangest thing. Even the Shapley concentration is not stationary. It too is moving. It too is being pulled. By what? By the average gravitational pull of even more distant matter, all of which is also moving, all of which is also being pulled by something further. The pattern repeats at every scale. Wherever you find a mass concentration, you find that it is part of a larger pattern of flow drawn toward an even larger mass concentration, which is in turn part of an even larger pattern. There is no anchor. There is no stationary point in the entire mapped universe from which the rest of the motion can be measured against a fixed background. The only thing that comes close to a stationary reference is the cosmic microwave background itself, the leftover light from the Big Bang, which fills the universe almost uniformly in every direction. Our local group is moving at 630 kilometers per second through this reference frame. Every other galaxy in the local universe is moving at some peculiar velocity relative to the same reference. The motions are everywhere. The stillness is nowhere. But there is something even stranger about the motion of our local group through space. Because it is not just being pulled by the Shapley concentration, it is also being pushed. In 2017, the team led by Yehuda Hoffman, Daniel Pomerade, R. Brent Tully, and Hélène Courtois published a paper in the journal Nature Astronomy. They were mapping the three-dimensional velocity field of the local universe in unprecedented detail, using a catalogue of galaxy peculiar velocities called Cosmic Flows 2. The map showed all the familiar features: the pull toward the great attractor and the Shapley concentration, the flow of galaxies toward the densest regions of the cosmic web. But the map also showed something new, something that had been suspected but never confirmed. There was a region of space, almost directly opposite the Shapley concentration, where galaxies were not flowing toward, they were flowing away from. And the rate of that outflow could not be explained by anything visible in the region. The space in that direction appeared, at first glance, to be empty. Hoffman and his colleagues realized what they were looking at. They were looking at a void, a vast region of underdensity, larger than any void previously mapped, and the void was acting like a repulsive force on the surrounding galaxies. Not because voids actually push in any physical sense. They do not. There is no anti-gravity. But the absence of mass in the void meant that galaxies on the near side of the void were experiencing less gravitational pull in that direction than they would otherwise have. The galaxies were being pulled slightly less toward the empty region. The net effect, when you add up all the gravitational pulls and pushes from every direction, was a flow that pointed away from the void and toward the Shapley concentration on the other side. They called the void the dipole repeller. The name describes the function. The void sits at one end of an imaginary line passing through our local group. The Shapley concentration sits at the other end. Together they form a dipole. The Shapley side pulls. The dipole repeller side, by being empty, pushes by absence. The combined effect of the pull and the push is the dominant motion of our local group through the cosmic microwave background. To understand why a void can effectively push, you have to think carefully about how gravity works in the cosmic context. Gravity is always attractive. There is no anti-gravity in any standard model of physics. A void contains less matter than the average region of space, and so its gravitational pull is weaker than the gravitational pull of the surrounding regions. From the perspective of any galaxy in the universe pulls on it from every direction at once. In a perfectly uniform universe, all these pulls would cancel out, and the galaxy would have no net motion. In a universe with structure, the pulls do not cancel. The galaxy moves in the direction of the strongest pull, which is the direction of the densest mass concentration nearby. If there is a void in the opposite direction from a mass concentration, the pull from the void's direction is weaker than the pull from the mass concentration's direction. The galaxy moves more strongly toward the mass concentration than it would otherwise have, because the void has less mass to pull it the other way. The net effect is as if the void were pushing the galaxy away. The push is not real in the sense of a repulsive force. It is the absence of a pull that would have balanced the pull from the other direction, but the effect on the galaxy's motion is the same as if the void were actively pushing. The dipole repeller is enormous, hundreds of millions of light years across. It contains very few galaxies by the standards of the cosmic web. It is one of the largest known voids in the local universe, and it has been there, in that exact location, exerting its gravitational absence on everything around it, for billions of years. We are being pulled and pushed simultaneously. The pull comes from the Shapley concentration. The push comes from the dipole repeller. Both forces are gravitational. Both forces are invisible to direct observation, in the sense that we cannot see the void any more than we can see the gravity of the cluster. We know they are there because of how everything moves. This is the deeper picture of our motion through space. We are not just being carried by the rotation of the Earth, the orbit of the planet, the spin of the solar system around the galactic center. We are also being carried by the gravitational flow of the entire local universe. The flow is shaped by mass concentrations like the Norma cluster and the Shapley concentration. The flow is shaped by absences of mass like the dipole repeller. The flow is older than anything in human experience. And the flow does not stop at our cosmic neighborhood. It extends in ways we are only just beginning to map, far beyond the boundaries of anything we have ever named. Pull back from our local group for a moment. Pull back from the Milky Way. Pull back from the cluster of galaxies that includes our galaxy and Andromeda and the dozens of smaller satellites that orbit them. Look at the region of space that contains all of these objects, and the Great Attractor, and the Norma cluster, and the closer arms of the Shapley concentration. Look at the region that contains everything our motion is connected to. That region has a structure. It has boundaries. It has a shape that has only recently been recognized. It is called Laniakea. And our entire cosmic address has to be rewritten to fit inside it. For most of the history of astronomy, the structure of the universe at the largest scales was a question without an answer. We knew there were galaxies. We knew galaxies were sometimes grouped into clusters. We knew clusters were sometimes grouped into larger structures called superclusters. But the boundaries between superclusters were vague. The definitions were imprecise. Astronomers would draw maps of the local universe and label different regions as different superclusters, but the labels were essentially arbitrary. There was no rigorous way to say where one supercluster ended and another began. In September of 2014, a team led by R. Brent Tully at the University of Hawaii published a paper in the journal Nature that changed how cosmologists thought about cosmic structure. The paper proposed a new definition of a supercluster, based not on the visual appearance of galaxies clumped together, but on something more physical, on gravity itself, on the directions galaxies were flowing. The idea was elegant. Imagine a watershed. A geographical watershed is the region of land within which all the rainwater drains toward the same point. If you stand on one side of a mountain ridge, the rain falls and flows down to one river. If you stand on the other side of the ridge, the rain flows down to a different river. The ridge is the boundary. The watershed is defined by the direction of the flow. Tully's team applied the same logic to the cosmic flow of galaxies. They asked, for every galaxy in the local universe, in which direction is it flowing under the combined gravitational influence of everything around it? They used a catalogue of peculiar velocities, the same kind of velocity data that had revealed the Great Attractor, but with more galaxies and better measurements than ever before. They mapped the three-dimensional flow of every galaxy they could measure, and they found that the flows formed coherent patterns, vast regions where every galaxy was flowing toward the same gravitational center, boundaries where the flows changed direction, where galaxies on one side were flowing toward one center and galaxies on the other side were flowing toward a different center. Those boundaries defined the watersheds. The volumes inside the boundaries defined the superclusters. When they applied this definition to our region of space, they discovered that our cosmic address was much larger than anyone had realized. The local group, the Virgo cluster, the Norma cluster, the entire region we had previously thought of as separate structures, were all part of a single, vast flow basin. Every galaxy inside that basin was being pulled gravitationally toward the same general region. The boundaries of the basin were defined by the watershed lines, the places where the flow switched direction. The team named the structure Laniakea. The word is Hawaiian. It means immense heaven, or in some translations, spacious heaven. The name was chosen as a tribute to the Polynesian navigators who used the stars to cross thousands of miles of open ocean, finding islands they could not see by reading patterns in the sky. Laniakea is enormous. 520 million light-years across, about 100,000 galaxies inside it. The total mass within Laniakea is roughly 100,000 trillion times our home star's mass. Our Milky Way galaxy sits on the outer edge of Laniakea, in a thin filament that connects to the main body of the supercluster. We are not at the center, we are at the edge of one of the largest known gravitationally coherent structures in the universe. The center of Laniakea is the Great Attractor. The Norma cluster sits there, the dense gravitational core toward which everything inside Laniakea is flowing. The Virgo cluster, where our local group is being pulled, is one of the major structures within Laniakea. The Centaurus cluster, the Hydra cluster, the Antlia cluster, the Fornax cluster, all of these well-known structures, all of them are inside Laniakea, all of them are part of the same gravitational basin, all of them are flowing toward the same destination. To grasp the scale, think about what 520 million light-years actually means. Light travels at about 186,000 miles per second. In 1 year, that adds up to about 6 trillion miles. The distance to the nearest star, Proxima Centauri, is about 4¼ light years. That is 25 trillion miles. The diameter of the Milky Way is about 100,000 light years. That is roughly 600 quadrillion miles, a number so large that the word for it does not have a familiar meaning. Now multiply that by 5,000. That is the diameter of Laniakea. 5,000 Milky Ways laid end to end. Each one of those Milky Ways contains hundreds of billions of stars. Each star has its own planets. Each planet, if it is in the right zone around its star, might have its own version of life. The number of stars inside Laniakea is something like 10 to the 15th power, 1,000 trillion, a quadrillion. This is your home. Not the planet, not the solar system, not the galaxy, Laniakea, the watershed of your cosmic address. And there is a strange beauty in the way Tully's team defined it. Laniakea is not defined by what is in it. Laniakea is defined by what its contents are doing. Specifically, by the fact that everything inside it is falling toward the same place. The structure exists because of the motion. Without the motion, there would be no boundary. Without the boundary, there would be no supercluster. Laniakea is a flow. To appreciate how strange this definition is, consider how we usually identify objects. A galaxy is a thing you can see. A star is a thing you can see. A planet is a thing you can see. We define these objects by what they are, by their physical composition, by the shape and structure they hold. The boundaries between them are sharp. Where the galaxy ends and intergalactic space begins is a question with an answer, even if the answer requires you to specify what you mean by the galaxy's edge. A supercluster, in the old definition, was supposed to be the same kind of thing. A region of space where galaxies were clumped more densely than average. The boundary was wherever the clumping ended and the average density resumed. But the old definition turned out to be problematic because the clumping does not have sharp boundaries. There is no clean line between dense regions and average regions. The cosmic web is connected, with filaments running from cluster to cluster, and any boundary you draw is somewhat arbitrary. Tully's team replaced the visual definition with a kinematic one. A supercluster in their definition is a region of space where the gravitational flow of galaxies points to a common attractor. The boundary is wherever the flow changes direction. This definition is sharper than the visual one, because flows have definite directions, and the boundary between two flows is a definite surface in three-dimensional space. The implications are subtle but significant. Under the new definition, Laniakea is not a stable object. The galaxies inside Laniakea are not held together permanently by their gravity. Many of them will, over cosmic time, be pulled away by the expansion of the universe before they can fall all the way to the great attractor. The structure is a snapshot of motion. The snapshot is meaningful right now, in the current epoch. The snapshot will not be meaningful in the deep future, because the motions will have changed and the boundaries will have moved. There is something philosophically interesting in this. We are defining one of the largest structures in our cosmic neighborhood not by what it is made of, but by what it is doing. The structure is a verb more than a noun. It is a process that creates the appearance of a thing. Imagine the cosmic web as a vast network of rivers with galaxies as the water. Each river has tributaries that pour into it. Each river drains into a larger flow. The watersheds, where one river system gives way to another, are the boundaries of the superclusters. Inside Laniakea, every galaxy is flowing toward the Great Attractor. Outside Laniakea, galaxies are flowing toward other attractors, other centers, other watersheds. Where does Laniakea end and the next supercluster begin? The boundaries of Laniakea are not perfectly sharp. They are statistical. They are the places where the gravitational flow shifts from pointing inward toward our Great Attractor to pointing outward toward another supercluster's center. The team identified several neighboring superclusters that share borders with Laniakea. Beyond the boundary in one direction is the Perseus-Pisces supercluster. Beyond another boundary is the Coma supercluster. Beyond a third is the Shapley supercluster, where the deeper pull of our motion ultimately originates. The Perseus-Pisces supercluster is a long, narrow structure that lies roughly in the opposite direction from Laniakea's center. It contains the Perseus cluster, one of the most prominent galaxy clusters in our cosmic neighborhood, and several other large clusters. Galaxies inside Perseus-Pisces flow toward their own gravitational center, not toward our Great Attractor. The watershed between Laniakea and Perseus-Pisces is a curving surface in three-dimensional space, marking the line where galaxy motions switch from flowing one way to flowing the other. The Coma supercluster, in another direction, is anchored by the famous Coma cluster, one of the densest and most thoroughly studied galaxy clusters in the local universe. The Coma cluster contains over 1,000 galaxies in a relatively compact volume, and it was one of the first places where astronomers found clear evidence for the existence of dark matter based on the high velocities of the galaxies inside it. Like Perseus-Pisces, the Coma supercluster pulls its own galaxies toward itself, defining its own watershed, distinct from ours. The Shapley supercluster, the most massive concentration in our region of the universe, lies outside Laniakea. It is in its own gravitational basin, with its own watershed boundaries. But the influence of the Shapley supercluster is so great that it pulls on galaxies far beyond its own borders. It pulls on us, on the entire Laniakea structure, even though we are not technically part of it. This creates a layered hierarchy. Laniakea is our home supercluster. Laniakea is part of a larger pattern, a network of nearby superclusters that influence each other. The Shapley supercluster sits in the middle of that network, the gravitational heart of our larger cosmic region. Some astronomers have proposed that Laniakea should be considered a substructure within an even larger system called the Pisces-Cetus supercluster complex, or sometimes the Shapley supercluster cocoon. The names are still being argued over. The structures themselves are real. The structures are real, and the flows are real, and the motions are everything we have been describing. Inside Laniakea, our Milky Way is moving toward the Great Attractor at about 600 kilometers per second. The local group is doing the same. The Virgo cluster is doing the same. Every galaxy inside the boundaries of Laniakea is participating in the same vast inflow toward the same dense center at speeds that would be incomprehensible at human scale, but are routine at cosmic scale. But Laniakea itself is not stationary. Laniakea is also moving. The entire structure, with all its 100,000 galaxies, is being pulled toward the Shapley supercluster, which lies just outside its boundary. The internal motion of galaxies within Laniakea, the inflow toward the Great Attractor, is happening on top of a larger flow that carries the whole supercluster in the direction of Shapley. You can think of it like a river flowing into a lake, while the lake itself is being slowly tilted, so that the whole body of water is also sliding sideways. The galaxies inside Laniakea are flowing into the Great Attractor. The Great Attractor and Laniakea around it are sliding toward the Shapley concentration. The motions are nested, The flows happen at multiple scales simultaneously, and the Shapley concentration is not stationary either. The Shapley concentration is moving as part of an even larger flow, one that includes superclusters across hundreds of millions of light-years of space. The mapped flow extends to a scale of perhaps 2 billion light-years. At that scale, the flow patterns become hard to measure because the peculiar velocities are small compared to the cosmic expansion, and our data on distant galaxies is less precise. But the pattern continues. Wherever we have managed to map carefully, we find more flow, more motion, more pulling towards something deeper. There may be a limit to this. There may be a scale at which the universe becomes statistically uniform, where the peculiar velocities average to zero, where the cosmic expansion is the only motion that matters. The standard model of cosmology predicts that this happens somewhere on the scale of a few 100 million light-years, beyond which the universe should look the same everywhere, with no large-scale flows. But every time we have looked more carefully, the flows have continued further than the model predicted. The local group is part of Laniakea. Laniakea is part of a larger flow toward Shapley. Shapley is part of even larger flows toward concentrations we are only beginning to map. The hierarchy seems to keep going. There was a controversial claim made in 2008 by the astronomer Alexander Kashlinsky and his colleagues that they had detected a phenomenon they called dark flow. The claim was that galaxy clusters across a vast portion of the observable universe were all flowing in the same direction, at speeds that could not be explained by anything visible inside the observable universe. The implication, if the claim were correct, was that something outside the observable universe was exerting a gravitational influence on everything inside it. The dark flow claim was, and remains, deeply controversial. Subsequent measurements from the European Space Agency's Planck satellite did not confirm the original signal at the strength Kashlinsky reported. The mainstream view today is that dark flow, in its strongest form, is probably not real. The galaxies inside our observable universe do flow in patterns that we can map, but the flows are explained by mass concentrations we can also map, including the Shapley concentration and the dipole repeller and various other features of the cosmic web. The case for some additional, harder-to-explain flow at the largest scales has not been definitively resolved. Some researchers continue to find statistical hints of bulk motion beyond what conventional gravity should produce. Most cosmologists treat these hints as inconclusive. The question of whether there is anything genuinely strange about cosmic motion at the largest mapped scales remains open. It is one of the questions that future telescopes and surveys will help to answer. What is certain is the motion at our local scale, the motion of the Milky Way through the cosmic microwave background rest frame, the flow of our local group toward the great attractor, the flow of Laniakea toward the Shapley concentration. These motions are not in doubt. They have been measured by multiple independent teams using multiple independent techniques. They are real. They are happening right now. You are inside Laniakea. The Milky Way is part of the inflow toward the great attractor. The entire structure is being carried toward Shapley. And while you sit in your chair, while you breathe and blink and think, every cell in your body is participating in all of these motions simultaneously. The rotation of the Earth, the orbit around our home star, the motion of that star through the galaxy, the motion of the galaxy through the local group, the motion of the local group through Laniakea, the motion of Laniakea through the larger cosmic web, the motion of the cosmic web itself through whatever larger structure contains it, if any larger structure exists. You are at the center of a stack of motions that nest into each other like the layers of an onion. Each motion is invisible to you, because you share it with everything immediately around you. But the motions are there. They are real. They have been there for as long as you have existed, and for billions of years before you existed, and they will continue to exist for billions of years after you are gone. The simplest description of what you are doing right now, in the most physical and accurate sense, is this. You are falling toward the great attractor. You are being pulled toward the Shapley concentration. You are being pushed by the dipole repeller. You are spinning with your planet. You are orbiting with your solar system. You are sweeping around the galactic center with the entire Milky Way. And all of these things are happening at speeds that, if you could feel them, would make every previous concept of motion in your life seem trivial. The image that emerges from this is unsettling. We have always pictured the universe, in our mental image of it, as a vast space in which objects move, like a sea, with currents and tides and the occasional whirlpool. But the picture is wrong. The objects do not move through a stationary space. The space itself is full of patterns. The patterns are the flows. The flows are the motions. The motions are the universe. There is no underlying stillness against which the motions can be measured. There is only motion, all the way down to the smallest scales and all the way up to the largest. What does the universe look like from outside this motion? It does not look like anything. There is no outside. There is no fixed reference frame from which the entire cosmic flow can be observed as a coherent picture. The closest we can come is the cosmic microwave background, the leftover light from the Big Bang, which fills space almost uniformly and provides a kind of reference grid. Our motion through that grid is measurable. Our motion through that grid is 630 kilometers per second. But the grid itself is not really fixed. It is the average state of an enormous number of photons, all of which are moving, all of which are doing what photons do, which is travel forever at the speed of light. Even the closest thing we have to a still backdrop is, at its smallest level, in constant motion. The question of what is actually pulling all these things, what makes the gravitational flow work in the first place, takes us to the deepest layers of cosmic motion, to the contest between two forces that, more than any other, determine what the universe will eventually become. Because while everything in Laniakea is being pulled toward the great attractor, the universe as a whole is doing something else. The universe as a whole is expanding, and the expansion is accelerating. The two motions, the local pull and the cosmic expansion, are in tension. They are not friendly, they are fighting. And the outcome of that fight, which is being decided right now, in the present moment of the universe, determines whether motion continues forever or whether it eventually wins out against itself and stops. Every motion we have described so far has been caused by gravity. Gravity pulled the Milky Way toward the great attractor. Gravity assembled the Norma cluster and the Shapley concentration. Gravity defined the watershed boundaries of Laniakea. Gravity is the engine of cosmic motion, but gravity is not the only force shaping the universe. There is another force, or something that behaves like a force, that has been working against gravity for billions of years. We do not know what it is. We do not have a satisfying theoretical explanation for it. We can measure it, and we have given it a name. We call it dark energy. Dark energy is the term astronomers use for whatever is causing the expansion of the universe to accelerate. In the late 1990s, two independent teams measured the distances to very distant supernovae and found something they did not expect. The universe was not slowing down, as everyone had assumed it would be. The universe was speeding up. The galaxies on the largest scales were receding from each other faster than they had been in the past. The expansion was not coasting from the Big Bang's initial push. It was being driven by something, by an energy that fills space, that has the strange property of getting stronger as space expands, and that pushes everything in the universe further apart. In the framework of general relativity, dark energy is often represented as a property of space itself, a kind of intrinsic pressure built into the vacuum that exerts a repulsive effect at cosmic distances. Where ordinary matter and dark matter pull things together through gravity, dark energy pushes things apart. And the further apart two objects are, the more dark energy there is between them, and the stronger the push becomes. The actual nature of dark energy remains one of the deepest unsolved problems in physics. We do not know if it is a true cosmological constant, the kind Einstein originally proposed in his field equations, or if it is something more dynamic, a field that changes over time. If it is a true cosmological constant, then the density of dark energy is the same at every point in space, and remains the same as space expands. As more space is created by the expansion, more dark energy comes into existence with that new space, while the density of ordinary matter and dark matter decreases. This is why dark energy becomes more important over cosmic time. Matter gets diluted by expansion. Dark energy does not. Eventually, in this picture, dark energy comes to dominate the energy budget of the universe entirely, driving the expansion to ever greater acceleration. If dark energy is not a true constant, but a field that varies over time, the future of the universe becomes harder to predict. Some models suggest that dark energy could grow stronger over time, eventually accelerating the expansion so violently that it tears apart galaxies, stars, planets, and eventually atoms themselves, in an end called the Big Rip. Other models suggest that dark energy could weaken over time, allowing gravity to eventually redominate and pull the universe back together in a big crunch. The current data slightly favors a constant, or nearly constant, dark energy. But the question is not closed. Surveys like the Dark Energy Spectroscopic Instrument are still gathering data that may, over the next several years, refine our understanding of what dark energy is actually doing. For the purposes of our story about motion, the key point is that dark energy is acting against gravity at the largest scales. It is the force that prevents the cosmic flows we have been describing from continuing indefinitely. It is the reason why Laniakea will not collapse onto the Great Attractor in any meaningful sense, and why the Shapley concentration will not gather the rest of the local universe into a single supercluster. The flows exist now because the structures are still close enough together for gravity to dominate locally. Over deep time, dark energy wins. This is one of the great ironies of modern cosmology. Gravity, the force we are most familiar with, the force that shapes every motion you have ever directly observed, is losing the contest at the largest scales. The unfamiliar force, the one we do not yet fully understand, is the one that determines the long-term future of the universe. We live inside the small remaining era when gravity still organizes our cosmic neighborhood. In the deep future, gravity will be confined to ever smaller bound systems, while the rest of the universe expands away beyond any possible interaction. This sets up the great cosmic tension. At every scale of the universe, two forces are in competition. Gravity pulls, dark energy pushes. The outcome depends on which force is stronger at any given scale. At small scales, gravity wins. The electromagnetic and nuclear forces hold atoms and molecules together against any push from dark energy. The gravitational binding of planets to their stars, and stars to their galaxies, and galaxies to their clusters is far stronger than any dark energy effect could overcome. You are not slowly being torn apart by the expansion of the universe. The space inside your body is not expanding. The space inside the solar system is not expanding. The space inside the Milky Way is not expanding. At these scales, gravity has won the fight, and the structures it has built are stable. At medium scales, the question gets more interesting. Galaxy clusters are gravitationally bound. The galaxies inside a cluster are held together by their combined gravity, and dark energy is not strong enough to tear them apart. But superclusters are different. Laniakea, our home supercluster, is not actually gravitationally bound. The galaxies inside it are flowing toward the great attractor, but most of them will never actually reach it. Dark energy is pulling them away faster than gravity can pull them in. Laniakea is, in a sense, an illusion of permanence. It looks like a structure because the flow patterns are coherent, but the flow is losing. Over billions of years, the galaxies in Laniakea will be pulled further and further from each other by the accelerating expansion. The flow will continue, but the distances will grow faster than the flow can close them. At large scales, dark energy dominates completely. Beyond the gravitationally bound clusters, the universe is dispersing. Galaxies that were once neighbors are now separated by hundreds of millions of light years. Galaxies that are too far away to be bound to anything will, eventually, be carried beyond the reach of any other galaxy in the universe. They will, from the perspective of any observer in our cosmic neighborhood, recede past the cosmic horizon and become forever invisible. This is the deep contest. Gravity working everywhere, trying to pull everything together. Dark energy working everywhere, trying to push everything apart. The two forces operate at different scales. The outcome, at any given scale, depends on which force is locally stronger. The expansion of the universe affects the local motion we have been describing in a specific way. The galaxies inside Laniakea are flowing toward the great attractor at hundreds of kilometers per second. But the space between them is also being stretched. Over very long time scales, the stretching wins. The flow is, in some sense, a temporary phenomenon. Given enough time, every galaxy in Laniakea will be carried by the cosmic expansion to a distance from which it can no longer feel any other galaxy's gravity. The flow will end. The supercluster will dissolve. We are living, right now, in the era when the flow still exists. The local motions are still strong enough to define a structure. The great attractor is still pulling our local group inward faster than the cosmic expansion is pulling us apart. But this era will not last forever. In a few tens of billions of years, the situation will change. The expansion will accelerate further. The gravitational pulls will weaken. The structures we live inside will begin to come apart, and a different kind of universe will emerge. But before we follow that path further into the future, we have to address something closer, something that has been part of the popular understanding of cosmic motion for over 100 years. The collision between our galaxy and our nearest large neighbor. The Andromeda Galaxy lies about 2.5 million light-years from the Milky Way. It is the closest large galaxy to our own. It is roughly comparable in size to the Milky Way, or possibly slightly larger depending on how you measure. Like our galaxy, Andromeda is a spiral. Like our galaxy, it contains hundreds of billions of stars. It is the largest member of our local group, along with the Milky Way itself. Andromeda is moving. Specifically, Andromeda is moving toward us. The two galaxies are approaching each other at about 110 kilometers per second. This much has been known since the early 20th century, when astronomers first measured the radial velocity of Andromeda and found it to be a blue shift instead of a red shift. Most galaxies in the universe are receding from us due to the cosmic expansion. Andromeda is one of the few that is approaching, because it is close enough that the local gravitational pull between our two galaxies is stronger than the cosmic expansion at that distance. For most of the 20th century, the assumption was that Andromeda and the Milky Way were on a collision course. The radial velocity was easy to measure. The transverse velocity, the sideways component of Andromeda's motion, was much harder to measure because it required tracking Andromeda's position on the sky over very long time periods and looking for tiny shifts. Without good measurements of the transverse velocity, astronomers could not say whether the two galaxies were heading for a direct collision or for a glancing pass. In 2012, a team led by Roland van der Marel and Tony Sohn at the Space Telescope Science Institute published the first measurement of Andromeda's transverse velocity based on years of Hubble Space Telescope observations. Their conclusion was that the transverse velocity was small enough that, when combined with the radial velocity, it implied a direct collision. The two galaxies, they estimated, would collide in about 4.5 billion years, producing a merger that astronomers nicknamed Milkomeda. The merged galaxy would be an elliptical, formed from the debris of the two original spirals, with most of the original stars surviving but redistributed. This finding became textbook material. The 4.5 billion year timeline became a fixed reference point in popular astronomy. Documentary after documentary described the inevitable collision. Many people who learned about it found it strangely comforting, in a way. The universe has a definite future. We know what is going to happen. In June of 2025, a team led by Till Sawala at the University of Helsinki, working with collaborators including Carlos Frenk at Durham University, published a new analysis that significantly changed the picture. They used updated data from both the Hubble Space Telescope and the Gaia Space Telescope. They ran 100,000 simulations of the future motion of the local group, including not just the Milky Way and Andromeda, but also the Triangulum Galaxy and the Large Magellanic Cloud, two smaller galaxies whose gravitational influence had been underestimated in earlier analyses. The results were genuinely surprising. The probability of a direct collision between the Milky Way and Andromeda in 4 to 5 billion years in the new analysis was only about 2%. 2%. Not the near certainty that previous textbooks had presented. The probability of any kind of collision or merger in the next 10 billion years was about 50%, a coin flip. The other half of the simulated scenarios showed the two galaxies passing each other, sometimes closely, sometimes more distantly, without merging on the timescales considered. The Large Magellanic Cloud, in particular, turned out to matter much more than astronomers had previously thought. The Large Magellanic Cloud is a satellite galaxy of the Milky Way, with about 15% of our galaxy's mass. Its gravitational pull, acting on the Milky Way over billions of years, perturbs our trajectory in ways that often steer the Milky Way away from a direct collision course with Andromeda. The Triangulum Galaxy, on the other hand, tends to increase the probability of a merger. The textbook future of our galaxy is, as of 2025, an open question. There is roughly equal probability that we collide with Andromeda within the next 10 billion years, and equal probability that we do not. The future of the Milky Way is not the inevitability that earlier generations of astronomers had described. It is a probability distribution, a range of possible outcomes, each consistent with the data, each playing out over timescales so long that no human will ever see them. But this uncertainty about the local fate does not change the larger picture of cosmic motion. Even if the Milky Way and Andromeda do not directly collide, they will still interact gravitationally for billions of years. The two galaxies are bound. The local group is bound. Whatever happens to our galaxy in the long term, our entire cluster of galaxies will remain connected, isolated together as the rest of the universe accelerates away. This is the future that dark energy guarantees. Whether or not the Milky Way collides with Andromeda, the local group as a whole will be cut off from the rest of the universe. The galaxies beyond our cluster, including the entire Laniakea supercluster, will recede from us as the cosmic expansion accelerates. The Great Attractor will become unreachable. The Shapley concentration will become invisible. The cosmic flows that connect us to the rest of the universe will be stretched until the flows stop being meaningful. In about 150 billion years, according to current models, every galaxy outside our local group will have receded beyond what cosmologists call the cosmic event horizon. The event horizon is the distance beyond which light from a receding source can no longer reach us, because the expansion of space between us and the source is faster than the speed of light. Galaxies beyond the event horizon are not just far away, they are unreachable. No signal from them can ever cross the gap. They are, for all practical purposes, in another universe. After a few 100 billion years, the night sky from any planet inside the local group will look very different from the night sky we see today. The stars of the Milky Way, or the merged Milkomeda if a collision happens, will still be there. The smaller satellite galaxies will still be there, in some form. But beyond our cluster, nothing. The rest of the universe will have receded into the cosmic horizon, leaving the night sky empty of any external structure. An observer at that point, looking out, would see only their own galaxy. They would have no way to know that anything else had ever existed. Consider what this means for the science of cosmology itself. Most of what we know about the universe comes from observing distant galaxies, the expansion rate, the composition of matter and energy, the age of the universe, the existence of the cosmic microwave background as evidence for the Big Bang. All of these conclusions depend on being able to see far away. If a civilization arose in the deep future, after the rest of the universe had receded beyond the cosmic event horizon, that civilization would look up at the sky and see only its home galaxy. The cosmic microwave background would have cooled to a temperature so low that it would not be detectable. The redshift of distant galaxies would be undetectable because there would be no distant galaxies to detect. Such a civilization, no matter how scientifically advanced, would have no way to discover that the universe was ever larger than their galaxy. They would have no way to learn about the Big Bang. They would have no way to map the cosmic web. They would assume, reasonably, that their galaxy was the entire universe, drifting in an infinite void. The cosmological knowledge that we currently possess would be permanently lost to them, not because of any failure of intelligence or curiosity, but because the evidence would no longer be available. We are, in this sense, living in a uniquely privileged epoch. An epoch when the universe is large enough to have produced structure, but young enough that the structure is still visible. The window for cosmological discovery is open. It will not be open forever. Some astronomers have pointed out the strange implication of this. We are living in a special era. An era when the cosmic structure is still visible. An era when telescopes can see distant galaxies. An era when the history of the universe is still readable, written into the light that travels to us from billions of years ago. In the deep future, this readability will be lost. Any civilization that arises in our cosmic neighborhood after the Great Recession will have no way to discover that the universe was ever larger than their own galaxy. They will live inside an island. They will assume the island is everything. We see the universe because we exist now. Earlier, the universe was too hot and dense to be transparent. Later, the universe will be too stretched and empty to show its history. The middle window, the window in which observation is possible, is the window we happen to occupy. The window will close. And once the cosmic structure has receded beyond the horizon, the local motions we have been describing will gradually unwind. The flow toward the great attractor will continue, on paper, but the great attractor itself will have been pulled too far away to gather anything. The motion of the local group through the cosmic microwave background rest frame will, in some sense, lose its meaning. The background itself will continue to fade as the universe expands. The reference frame that defined our motion will become harder and harder to measure. In trillions of years, the local groups of galaxies that remain in their isolated pockets, like the Milky system in our own region, will continue their internal dynamics. Stars will still orbit galactic centers. Dwarf galaxies will still orbit their hosts. Inside any bound cluster, motion will continue. But the larger cosmic flow, the rivers of galaxies that defined Laniakea, will be gone. The watershed will have evaporated. This is the long arc of cosmic motion. We live in an era of structure. The era is finite. The structure is being dispersed, slowly but accelerating, by the same force that drove the universe to its present state. The two motions, the local pull and the cosmic expansion, are different stories told at different scales. The local story is about galaxies falling toward gravitational centers, about the formation and persistence of structures bound by gravity. The cosmic story is about the dispersal of those structures, about the steady drift of everything away from everything else, about the eventual silence of the cosmic web. Both stories are happening right now. Both stories will continue to happen. The local story will dominate for tens of billions of years more before the dispersal becomes more important than the gathering. The dispersal will then dominate for hundreds of billions of years before even the dispersal stops being meaningful, and we enter the deepest phase of cosmic time. We need to talk about that deepest phase. Because while everything we have described so far has been motion, the eventual outcome of all motion is something else. The forces we have been describing eventually exhaust themselves. The structures eventually disperse. The stars eventually burn out. The black holes that ultimately consume what remains of organized matter eventually evaporate. And in the deep future, beyond all timescales that human imagination can comfortably hold, something is waiting that no living thing has ever experienced. The end of motion. The state that cosmic processes are slowly building toward. The state you have been imagining you already had, every time you sat in a chair and felt yourself to be still. Real stillness. The kind that arrives when every form of motion has, at last, given up. To understand where all motion is going, we have to talk about entropy. Entropy is one of the most important concepts in physics and one of the most misunderstood. It is usually described in popular accounts as a measure of disorder. That description is correct in a loose sense, but it can be misleading. A more precise definition is that entropy measures the number of microscopic arrangements that produce the same macroscopic appearance. A neat room has only a few ways to look neat. A messy room has many ways to look messy. The messy room has higher entropy. The second law of thermodynamics says that the total entropy of an isolated system never decreases. It always stays the same or increases. The universe, treated as an isolated system, must therefore have entropy that constantly grows over time. The arrow of time itself, the direction in which clocks move and people age and broken cups never reassemble themselves, is the direction of increasing entropy. The reason time has a direction at all is because entropy is growing. The universe began in a state of extraordinarily low entropy. The conditions of the Big Bang were, by any measure, highly ordered. The very smooth, very uniform distribution of energy in the early universe was a low entropy state, even though it looked, by everyday standards, like the maximum possible randomness. The clumping of matter into galaxies and stars, paradoxically, is a higher entropy configuration than uniform smoothness, because gravity makes structure favorable in entropy terms. The universe has been growing more entropic, more structured by gravity, more dispersed by dark energy for almost 14 billion years, and it will continue to do so until it reaches a state called thermodynamic equilibrium, the state of maximum entropy, the state in which no useful work can be extracted from any difference in temperature or energy density because there are no more differences. Every part of the universe is the same temperature. Every region has the same density. Every form of organized energy has been converted to disorganized heat. At thermodynamic equilibrium, motion stops. Not in the sense that individual atoms freeze in place. Atoms always vibrate at any temperature above absolute zero. But organized motion, the kind that produces structures, that powers stars, that drives the flows of cosmic gas, that holds galaxies together, ends. The universe, at equilibrium, is uniform. There are no gradients. There is nothing to flow from anywhere to anywhere else. The cosmic story is over. This state has a name. It is called heat death. The name is misleading because nothing dies in any biological sense, and the temperature is not particularly hot. The name comes from 19th century physics, when thermodynamics was first being developed, and the implications of the second law were first being worked out. The German physicist Rudolf Clausius and his contemporaries realized that if the universe was indeed governed by the second law, the eventual outcome had to be a state of maximum entropy. They called it heat death because they imagined it as a kind of cosmic thermal grave in which all of the universe's organized energy had been dissipated into uniform heat. Modern cosmologists still use the term, partly out of respect for the history, partly because no better name has emerged. The reality is stranger than the 19th century picture. The heat death of the universe will not be hot. It will be extraordinarily cold. The accelerating expansion driven by dark energy is stretching everything to lower and lower densities, including the photons that fill space. As space expands, photons lose energy. Their wavelengths stretch out, their frequencies drop, their effective temperatures decrease. The cosmic microwave background, currently at about 2 7/10 degrees above absolute zero, will continue to cool toward absolute zero as the universe ages. Heat death is more accurately described as cold death, or even better, as the slow approach to a state of maximum disorder, maximum dilution, maximum stillness. The path to that state is enormously long. Cosmologists have worked out approximate timelines for the major phases. Each phase is so much longer than the one before it that the present age of the universe, almost 14 billion years, is just the briefest flicker at the beginning of the story. We are currently in what some cosmologists call the stelliferous era, the era of stars. Stars are forming, stars are burning, stars are dying. New stars are being born from the gas left behind by the old ones. The universe is alive with stellar activity. This era began a few 100 million years after the Big Bang, when the first stars ignited, and it has continued ever since. It will continue for a long time yet, but not forever. The end of star formation will happen gradually. As stars age and die, they return some of their material to the interstellar medium, but they also lock up some of it permanently in compact remnants, white dwarfs, neutron stars, black holes. The available gas for forming new stars steadily decreases. After about 100 trillion years, the last star will form. That number, 100 trillion years, is so large that it bears repeating. The current age of the universe is a little under 14 billion years. 100 trillion is more than 7,000 times longer than the entire history of the universe so far. If you compressed the time from the Big Bang to the present into a single second, the time until the last star forms would still be about 2 hours. But the last star to form will be the smallest type of star. Red dwarfs are the most common stars in the universe. They are also the longest lived. A typical red dwarf burns its fuel so slowly, so efficiently, that it can shine for trillions of years. The smallest red dwarfs, the ones with the least mass and the slowest fusion rates, may shine for up to 100 trillion years individually. Imagine that. A single red dwarf, born quietly in some forgotten corner of a galaxy that has long since stopped forming new stars, burning at a temperature so low that its light is mostly infrared, sustaining its own fusion reactions for 100 trillion years. Our local star, by comparison, will burn for about 10 billion years total and is already about halfway through its life. The longest-lived red dwarfs will burn 10,000 times longer than our home star will. They will be the final stars, the last sources of light in the universe, the slow, patient endings of the stelliferous era. When the last red dwarf burns out, the universe enters the next phase. Some cosmologists call it the degenerate era, after the type of matter that dominates it. The era of stellar remnants, black holes, neutron stars, white dwarfs slowly cooling to black dwarfs. The universe is dark in this era because there are no more stars to produce light. The galaxies are still there in the sense that the gravitational structures persist, but their visible content has changed. The stars that defined them are gone, replaced by their remnants. The degenerate era lasts a very long time. Estimates suggest at least 10 to the 40th power years, that is 1 followed by 40 zeros. If the entire history of the universe so far were compressed into a single second, the degenerate era would last longer than the current age of the universe, repeated trillions of times. Some processes still happen during this era. Black holes still merge with each other occasionally when they encounter each other in the dispersing galaxies. White dwarfs continue to cool toward absolute zero, becoming black dwarfs, invisible objects that no longer radiate any meaningful amount of light. Neutron stars persist, slowly cooling. Some theories predict that protons themselves, the particles that make up the atomic nuclei in all ordinary matter, will eventually decay into smaller particles. If proton decay is real, all the matter that is not already inside a black hole will eventually dissolve into pure radiation and lighter particles over timescales of perhaps 10 to the 34th or 10 to the 40th power years. Whether protons decay or not is still an open question in particle physics. The decay has not been observed in laboratory experiments. If it occurs, it must happen on timescales far longer than any experiment can test. After the degenerate era comes the black hole era, the era when the dominant objects in the universe are black holes, stellar mass black holes formed from the collapse of massive stars, supermassive black holes at the centers of what used to be galaxies, black holes that have merged with other black holes over the deep time of the previous era. The black hole era is long, astonishingly long, because black holes, contrary to their reputation as eternal objects, are not eternal. In 1974, the physicist Stephen Hawking showed that black holes slowly evaporate, emitting a faint radiation, now called Hawking radiation, that carries away their mass over time. The evaporation is incredibly slow for any reasonably sized black hole. A stellar mass black hole with the mass of a few suns takes about 10 to the 67th power years to evaporate completely. A supermassive black hole with the mass of millions or billions of suns takes much longer. The largest supermassive black holes may take 10 to the 100th power years to evaporate. That number, 10 to the 100th power, is the number cosmologists sometimes write as a googol, a 1 followed by 100 zeros. These timescales are so enormous that they break ordinary human intuition. To get a sense of how absurdly long 10 to the 100th power years is, consider this. If you started counting at 1 and counted one number every second, it would take you about 32 years to reach a billion. To count to a trillion, it would take you over 30,000 years. To count to 10 to the 100th power, even at one number per second, you would need 100 trillion, 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 trillion times the current age of the universe. That is how long the last and largest black holes will take to evaporate. And during all that time, they are the only objects of significant mass in the universe. Slowly, incredibly slowly, hemorrhaging mass into the cold vacuum around them until they reach a point where they shrink fast enough to release the last of their mass in a final burst of radiation. The smallest black holes evaporate first, the largest last. Each one ends in a faint flash, releasing the final fraction of its mass as a burst of high-energy particles. And then it is gone. To picture what Hawking radiation actually involves, you have to think about the quantum vacuum. The vacuum in modern physics is not empty. It is full of virtual particles, pairs of particles, and antiparticles that appear briefly, exchange energy with the vacuum, and annihilate each other before they can be directly detected. This process is happening everywhere in the universe, all the time. Most of these virtual pairs come and go without producing any measurable effect. But near the event horizon of a black hole, something subtle changes. The intense gravitational gradient at the horizon can sometimes separate a virtual pair before they have time to annihilate. One particle falls into the black hole. The other escapes outward and becomes real. From the perspective of a distant observer, the escaping particle appears to have come from the black hole itself. The black hole has radiated. The mass of the particle, which came from somewhere, has come from the black hole's own mass energy, which has decreased by exactly the corresponding amount. This is the process Hawking worked out in 1974. The radiation is extraordinarily faint for any black hole large enough to detect directly. A black hole with the mass of our local star would emit Hawking radiation at a temperature so low that the radiation is utterly negligible compared to the background heat of the universe. Such a black hole, in our current epoch, is actually absorbing more energy from the cosmic microwave background than it emits through Hawking radiation. It is growing, not shrinking. The evaporation only begins to dominate once the cosmic microwave background has cooled enough that the black hole's faint emission exceeds what it absorbs. This cooling will take a long time. The universe currently has a background temperature of about 2 7/10 degrees above absolute zero, decreasing slowly as space expands. For stellar mass black holes to begin net evaporation, the universe will need to cool to billionths of a degree above absolute zero. This will take perhaps trillions of years. Once the cooling reaches that point, the black holes begin their slow decay. And once they begin, they continue inexorably for the rest of cosmic time. The shrinking is itself a process worth picturing. As a black hole loses mass, its event horizon shrinks. As the horizon shrinks, the temperature of its Hawking radiation increases. The relationship is inverse, which means that small black holes evaporate much faster than large ones. The very final moment of a black hole's existence is therefore explosive in a quiet way. Over the entire life of the black hole, the radiation is extraordinarily faint. In the last fraction of a second, the temperature spikes enormously, and the remaining mass is released as a burst of high-energy particles. The black hole, having existed for some enormous number of years, ends in a flash that lasts less than a moment. When the last black hole evaporates, sometime around 10 to the 100th power years from now, the universe enters its final phase. Some cosmologists call it the dark era. It is the era of nothing, almost literally nothing. The universe at this point is filled with the lowest energy particles that survive, photons, stretched to extraordinarily long wavelengths by the continuing cosmic expansion, neutrinos, drifting through space at near the speed of light, almost never interacting with anything. Electrons and positrons, the lightest charged particles, if they have not all annihilated with each other by then. And the radiation from the last black hole evaporations redshifting towards zero energy as space continues to stretch. There are no more stars. There are no more black holes. There are no more galaxies in any meaningful sense. The matter that was once organized into galaxies has been dispersed, decayed, evaporated, redshifted away. The universe is dilute beyond any reasonable description. The density of particles is so low that any given cubic meter of space is, on average, empty. Empty even of the radiation that filled space at earlier times, because that radiation has been stretched to wavelengths longer than the cubic meter itself. The temperature of the universe at this stage is essentially indistinguishable from absolute zero. The cosmic microwave background, the leftover heat from the Big Bang, has cooled to a temperature so close to zero that it cannot be meaningfully measured. The thermal motion that defines temperature has dropped to its quantum mechanical minimum. The universe has approached the state of maximum entropy. It has not quite reached it, because absolute equilibrium is technically a limit, not a state. But it has approached it so closely that, for all practical purposes, the difference does not matter. This is the end of motion. In the deep, deep future, when the last black hole has evaporated and the last particles have been stretched to vanishing wavelengths, the universe is as still as it will ever be. Not perfectly still. The quantum vacuum still fluctuates. Particles can still appear and disappear in random quantum events, on timescales determined by the uncertainty principle. The vacuum is not perfectly silent, but organized motion, the kind that defines life and structure and the flow of cosmic rivers, the kind that produces galaxies and stars and the orbital paths of planets, is over. The universe gave you motion before you were born. It will keep moving for billions and trillions and far longer after you are gone. But eventually, the motion runs out. The universe achieves the stillness you have spent your entire life imagining you already had. The stillness you have never actually experienced, not for a single second, not in any moment of your existence. This is the strange beauty of cosmic motion. The thing you assume you have, you do not have. The thing you assume you cannot have, the universe is steadily producing on a timescale you cannot imagine, through processes you cannot perceive. The motion that surrounds you, that you share with everything around you, that has carried you for every instant of your life, is finite. It will end. The universe will become what you have always pretended to be. Still, some people, learning about heat death, find it horrifying. They cannot stand the thought of an ultimate ending. The image of a cold, dark, empty universe, with no possibility of new motion or new life or new anything, strikes them as a kind of cosmic horror, the opposite of meaning. But there is another way to hold this picture. The universe is doing what physics requires it to do. The increase of entropy is not a moral failure of the cosmos. It is the natural direction of time. The slow approach to equilibrium is the slow approach to the most likely state, the state with the most ways of being. If you imagine all possible universes, weighted by how many configurations they could each have, the high entropy ones vastly outnumber the low entropy ones. The universe is heading toward where most of the possible universes are. It is heading toward the average. We live in a strange, atypical epoch. An epoch when the universe is still organized, when structures exist, when motion is still meaningful, when stars are still burning. This epoch is rare in terms of cosmic time. It is brief. It is the special phase between the very low entropy of the Big Bang and the very high entropy of the heat death. We exist in the only phase when entities like us could exist. The only phase when consciousness has the conditions to arise. Before us was too hot, too chaotic. After us will be too dispersed, too cold, too still. This is sometimes called the anthropic perspective. Of course, we live in the era of stars and structure and motion. It is the only era in which life is possible. The fact that we are here, observing the universe, is evidence that the universe is currently in a state that permits observers. The universe of 100 trillion years from now will not have observers, because nothing capable of consciousness will exist anywhere in it. The universe of 10 to the 100th power years from now will not have observers, because the conditions for any kind of organization have long since ended. We are not just temporary. We are exquisitely rare. We exist in the brief, glowing middle of the cosmic story, when the motion still means something, when the structure still has form, when the question of why things happen can still be asked by minds capable of asking it. Now we have to close the loop. We started this story at your body. We started with the strange fact that you are sitting still, even though the planet under you is spinning at hundreds of miles per hour, even though the solar system is hurtling through the galaxy at 500,000 miles per hour, even though the galaxy itself is being pulled toward the great attractor at over 1,000,000 miles per hour. We started by pointing out that stillness, as you have always experienced it, is not a physical state. It is a cognitive illusion produced by the fact that your senses are not equipped to detect uniform motion. We have now traveled to the end of cosmic time. We have followed the motion outward, through the structures it produces, through the forces that drive it, through the contest between gravity and dark energy that determines its outcome. We have seen Laniakea, our home supercluster, defined by the river of galaxies flowing toward the great attractor. We have seen the dipole repeller pushing us, and the Shapley concentration pulling us, and the larger cosmic web extending in every direction. We have seen the slow dispersal of structures as dark energy carries everything apart. We have seen the slow burnout of stars, the slow evaporation of black holes, the slow approach to maximum entropy. And we have arrived at a strange place. The end of all this motion, the destination toward which the entire cosmic story has been heading, is the state you have been falsely experiencing your entire life. Stillness. Not the illusion of stillness that your senses produce, the real thing. The cosmic equivalent, the state in which no atoms vibrate above their quantum mechanical minimum. No photons travel through any meaningful distance. No gravitational flows pull anything toward anything else. The universe, finally, doing nothing. That is where everything is going. Right now, while you read this, while you sit in your chair, while your body continues to participate in the rotation of the Earth and the orbit of the solar system and the motion of the galaxy and the inflow of Laniakea, the universe is slowly approaching the state of true rest. The motion that you cannot feel is heading toward an ending you will not be alive to see. The cosmic clock is running. Each tick of that clock, each fraction of a second of cosmic time, brings the universe slightly closer to its final state of stillness. You have one tiny window inside that clock. The window is your life. The window is also the entire history of human civilization, which is a flicker on the cosmic timescale. The window is also the entire history of life on Earth, which is barely longer. The window will close. The Earth will eventually be consumed by an expanding red giant phase of our home star. The solar system will eventually wander off into intergalactic space if the Milky Way and Andromeda merge, or it will be pulled apart over cosmic time even if they do not. The galaxy itself will eventually run out of star-forming gas and grow dark. The universe will eventually expand past the point where structures can exist. And in the deep future, after all of that has happened, the universe will finally be still. But not yet. For now, you are in the motion. You are part of it. You always have been. You always will be, for as long as you exist. There is something worth saying about this, if you can hold it without flinching. You have spent your entire life thinking of stillness as ordinary, as the default state of being, as the calm baseline from which all motion is a temporary departure. You sat in your chair and felt yourself to be at rest. The world moved around you, and you were the stable point in the middle. That was a story. The story was useful. The story let you function. The story let your brain conserve attention for things that mattered for survival on a small planet, near a small star, in a quiet corner of a moderate-sized galaxy. But the story was not true. The truth is that you have always been in motion. The truth is that motion is the natural state of everything that exists. The truth is that stillness is the rare condition, the exceptional condition, the condition that the universe is slowly assembling for itself over time scales that dwarf the age of every star you have ever seen. You are moving right now through something enormous, towards something we cannot fully name. The pull is invisible. The push is invisible. The flow that carries you is invisible. And yet, when you stop and let yourself think about it, the motion is the deepest fact about being alive in this particular universe. It is what you are. It is what every cell in your body has been doing since the moment of conception. It is what every atom in your body did before there was a you to assemble them. The motion that carries you also carries the light from the most distant galaxies. The same gravitational forces, the same cosmic flow, the same physical laws. You are not separate from the cosmic story. You are inside it. You are made of stardust, formed in earlier generations of stars, scattered across the galaxy by supernovae, gathered into the cloud that became the solar system, assembled into the chemistry of a single planet, organized through billions of years of evolution into the body that is now reading these words. And the motion you cannot feel is the same motion that built all of this. The same motion that will, eventually, take it all apart. There is one thing to do with this knowledge. It is not to be sad. It is not to be afraid. The universe has set the conditions. The conditions include motion at every scale, for as long as anything exists. The conditions also include the slow approach to a state where motion will end. On timescales that have nothing to do with us. The conditions are what they are. Our task, the task of any conscious being that emerges briefly inside the cosmic motion, is to notice, to pay attention to the motion that we are inside, to recognize, for the small window of our existence, that we are participating in something vast. You felt still when this began. You were not. You are not now. You will not be, for as long as you exist. The universe gave you motion before you were born, and it will take it back long after you are gone. In the meantime, you are moving, right now, through something enormous, towards something we cannot name. The pull is invisible. The push is invisible. The spiral path your body traces through the cosmic web is invisible. And that, for reasons that are difficult to explain, feels exactly like what life is supposed to feel like. Notice the motion. Notice that you have always been part of it. Notice that for the brief window of your existence, you are inside something far older and far stranger than the chair you are sitting in. Good night. May the motion carry you gently into sleep.